Welcome to the Geological Society of the Oregon Country Geology Talk. We are the oldest collaboration of amateurs and professional geologists in the Pacific Northwest. We have been pulling the car over at Outcrops for 87 years now, providing the Portland metro area and larger Oregon and Washington community with field trips and lectures. I'm going to start passing it over to our Program Director, Sheila Alfson, Professor Sheila Alfson, who's going to do a presentation later, to mention our next Friday night lecture or anything else that's coming up. Sheila, do you want to tell us what we can expect?
We have a great lineup headed up for you. So February, now we always meet the second Friday of every month, except if there is a special event. So the second Friday of every month. So the second Friday of February, we're going to have Lydia Staish from the USGS, and she is going to talk about the development of the Columbia River Plateau, the Columbia River drainage. So the Snake River used to join in a different location, join the Columbia River in a different location than it does now. And so she's going to talk about the development of it and what is responsible for changing the course of the river. And then March is our normal banquet. And so that isn't the second Friday of the month. And Clark, our president this year, the president is usually responsible for the March speaker at the banquet. So I'm going to turn it over to Clark. Are you still with us, Clark?
I'm still here.
There you go. Okay.
So I regret to have to inform you guys that the March banquet has been canceled, and that is my decision. And I've based that on the Omicron spike here in Oregon, and like many of you, COVID has run through my house. So I made the decision. We'll probably, instead of a banquet this time, is like we did last year, is have a speaker. And I have a speaker lined up, and he's Jason McClowry out of the Eastern Oregon office for the Department of Minerals, Geology and Mineral Industries. Jason is, in my opinion, will be one of the 5 top geologists that has worked in Oregon.
Jason is wonderful.
He has, along with his mentor, have probably boots have walked over most, if not all, of Oregon. And he is prolific in his publications. He's going to talk to us about 2 places. He's going to talk about his recent work at Hood River and the tectonics and the evidence that he's got for strike slip faulting in that graben out there. And then he's going to focus also, kind of a split his talk and talk of, thank you, honey, my granddaughter. And he's going to talk about the geology that we've done, and I've worked there too, north of Burns, and he's going to talk about a new caldera that they're starting to define out there. So that's what
that's wonderful. And just to clarify, Clark, does that mean that we get Jason for the Friday night lecture on Zoom?
We'll probably swing. Yes,
March.
He's agreed to do a Friday night lecture either in person or Zooming.
So that's always the second Friday of the month. And Sheila, the Dr. Staish presentation in February, will that also be on Zoom, or have we decided that yet?
That will be on Zoom. And let me just reiterate, for Clark didn't make that decision by himself. We all kind of did agree that it was a little too early to meet yet. And we are going through that for our Friday, the same decision making for our Friday night meetings. So Lydia Staish will be on February 11th, and it will be via Zoom. And now we're finding out that March will also. April is still up in the air, whether it will be Zoom or live. And we're hoping, again, we thought we'd be back to normal in-person meetings by January, but Omicron kind of put the glitch to that. So stay tuned, because we don't know.
And we appreciate that the decision was kind of hard to make, and thank you, Clark. I know we've had to make a couple of those decisions, as many clubs have, and we appreciate the patience of our members. So we also do field trips. We don't have Carol Hasenberg, our field trip director here. I suspect she's still in Hawaii, so she hasn't joined us. But is there anyone here who wants to talk about an upcoming field trip? I can talk about a couple of mine that might be happening. Clark, do you want to say anything, or Sheila, or anyone else from the club?
Well, I will give a short field trip, a one-day field trip across the Willamette Valley. And so if anybody is interested, it's just a one day, but we will start in the Coast Range and do an actual cross section of the Willamette Valley. And then I'll teach you, if you want, you don't have to turn this in for credit. But if you want to participate, I teach you how to make a cross section, a geologic cross section of the valley.
That's wonderful.
Yeah. So
And Clark, you seem to have been joined by another member. Do you want to introduce her?
My field partner here. This is my granddaughter, Ryan. And hopefully.
Hi, Ryan. Hi.
Hi, Ryan.
So we have on slate this year 7 field trips. And we are thinking, we're still working on the John Day, seeing if that will take place on the float trips that we had last year. They're not associated necessarily with us. They're a private company, but we have been using our platform as sort of a way to get people to participate. So I'm going to lead a trip in August, and we're going to go look at least at the lower Clackamas River Basin and the geology there. It starts from the Miocene and goes all the way up into to the present, of course. But there's interesting river terraces and other things that are tectonically related. If the roads are open and 224 is open, which is a highway that goes from northern Portland down to Detroit, which is about 50 miles. If that opens up, we'll look at the upper Clackamas Basin. The road is closed because of wildfires last year. And so that'll be I think one of the big trips we're going to have is a trip to Crater Lake, and it will be the first time GSOC is sponsoring a trip down there. So I think you'll find that there's a few interesting trips that we've got lined up this year.
I think it's going to be great. And membership in GSOC is required to attend those field trips. That's one good reason to become a member. Or we have some field trips. If you're not sure, like whether you're ready to join this group of people. I remember when my first field trip was one of Carol's field trips, and it felt like the first day of kindergarten to me. I was like, I don't know if I'm going to fit in with these people, if they're going to like me. And Larry Purchase was so nice to me and everything. We do have some smaller trips that we'll be doing in the Portland area. One of them is the East Side Bike Trip, which traditionally has been on the same day as the Portland Naked Bike Ride. We have not we can kind of count on good weather. You do need to be close. Yes, thank you for pointing that out. We do expect you to wear clothes unless you're, of course, engaging in political speech. And then the Oregon Supreme Court has ruled that you can be nude, but we would prefer for safety.
Do some people do that?
Point of order, excuse me.
Point of order.
A second Fred Shipley has just joined the meeting. Would you please turn your video on, sir?
Yeah, Fred, we want to make sure that we did have, and I'll mention this now, I think we tightened up our security, but we did have some youth that joined us last time and drew a penis on the whiteboard. And so one of the reasons you had to go through another hoop today was
that associated with the naked bike ride?
It wasn't at all. It was unrelated to any geological content.
You should hook them up. They should have their own group.
They had. So in any event, I'd lost my place. What was I talking? Oh, local trips. So we will have the East Side Bike Trip. We will have, it sounds like, Sheila, I've asked Jim O'Connor to help us with a local Portland Buttes trip. And
oh, wonderful.
So we'll see if that manifests, and we might do a downtown Building Stone geology trip if it looks like the virus has subsided enough so that I can be confident about scheduling that. I think that's it for field trips right now. One of the things that's been on our radar and is part of our mission as GSOC is education about earthquake resilience and preparedness. A couple of members, last year we worked on the Save Togami campaign, the Department of Geology and Mineral Industries. We were successful with that. This is not a GSOC project, but some of us, Yume Wang and myself, have been encouraging our senators to reintroduce legislation that would regulate the critical energy infrastructure. For those for whom this is new, the critical energy infrastructure, or CEI, is the fuel depots in Northwest Portland on the riverside through which 95% of the fuel for Oregon, the fossil fuels for Oregon, pass. And they're threatened in the event of earthquake because they're on fill that will where liquefaction will occur in an earthquake. And so the tanks will fail, releasing toxic fumes, catch fire, and float downriver, causing environmental catastrophe. Because of just the way the law and the 20th century and our use of fossil fuels evolved, they are more or less unregulated, for example, by building codes. And so we have pushed for the introduction of a bill, and Senator Denbrough and many other senators and representatives are supporting Oregon SB 1567. Does two things. Number one, it gives Department of Environmental Quality regulatory authority over the fuel tanks so that they can require that the companies that run the tanks have a seismic mitigation plan. They have a plan for shoring up the tanks and preparing for earthquake. And secondly, and this might be more controversial, but it gives Department of Energy authority to plan for distributing fuel throughout the state for emergency purposes. Because the second half of this is that not only will there be environmental catastrophe, but that fuel will be needed for reconstruction after an earthquake. Now, obviously, there are concerns that many have about reinforcing the fossil fuel infrastructure. For that reason, this plan will require falling into line with the regulations concerning greenhouse gases, but that will be in the hands of Department of Energy. So if you're interested in this, and this is not required by any means, but some of us are encouraging our senators. I called my senator, Senator Taylor, and I encouraged her to be a co-sponsor of the bill. If you're interested in contacting any of your Oregon, I'm sorry, for those of you who are outside of Oregon, you don't have to worry about this. That's one thing, you don't have to worry about it. If you're interested in contacting any of your Oregon senators or representatives, put your name in the chat, and we can chat subsequently about the way to do that, and we can give you some text if you want that provided. Send them an email, and I got a pretty good response back from not the senator herself, but her staff. So going to end there. Are there any other announcements? I'm not hearing any, so I think we're going to pass it to Sheila for Dr. Alson's Corner. She's going to give us a little presentation, and then we're going to hear from Andrew. We've had some really interesting geology news this week, so we'll hear from Andrew. And time permitting, we'll do a little show and tell after that. And Gary, how many folks do we have for show and tell?
Oh, I'm sorry. I'm so focused on the participant list. I don't know.
You've got about 20 minutes before you have to have an answer to that question. So keep doing the great work that you're doing, and welcome, Larry. We'd love to see your video and hear a little audio. Well, at least show us your video. We're not going to have you go on audio right now because we're going to pass the baton to Sheila and her presentation. Sheila, take it away.
Thank you, Paul. Paul, before we get started, I want to remind you, I gave up the hosting to you, and so you need to make Andrew a co-host so he can share his screen.
Thank you for reminding me that.
I was trying to find it on the chat so I could say that privately, but I couldn't find you. Anyway, and Andrew's got a great presentation. I'm looking forward to it. I'm just going to do a very quick one, and mine is old news now. Because a couple of months ago, we had earthquakes off the Oregon coast. And I figured people may people get alarmed at that, and rightfully so, because we are expecting a major subduction earthquake, which will cause a tsunami off the Oregon coast as well as other things. And so when the news starts talking about earthquakes off the coast of Oregon, people get nervous. I want to do just a quick presentation on why these particular types of earthquakes aren't the one to be feared. So this is good news, right? We all need a little bit of good news. So I have a little paper model. I take my cue from Tanya Atwater and J. Tuzo Wilson, who started out with plate tectonics using paper models. So I made a paper model, which I'm going to share with you. But first, I just want to talk a little bit about subduction. So if we want to characterize what Oregon is all about, and one major geologic process that shapes Oregon is this idea of subduction. So we have the Juan de Fuca plate subducting under the North American plate, and it gets stuck there. Okay, so where my fingers are touching, I don't know if you can see, but where my fingertips are touching the other plate, this gets stuck here. This causes the coast range to rise. And this is the position that we are in right now. Now, eventually, the strength of the pushing, the plate pushing, is going to exceed the strength of the rock to hold it, and it is going to snap. And that will create a subduction earthquake. Now we've got ocean over here. So when that happens and the plate snaps, the edge of it pushes up, which pushes up the bottom of the ocean. So it's like if I had a pan of water here in my hand and I did this and bumped it, it would rise up a blister of water and then spill over the edge. That's just basically what happens in a tsunami. And that's how a tsunami is generated. But let's look at my paper model and see how the earthquakes that happened last month or a couple months ago off the Oregon coast, how they are not going to cause that and why. So I'm going to switch to my document camera, and I put together a little model for you here. Okay, and I am going to change to speaker view so that I can see what I'm doing here, what I'm showing you.
Being good from our end, Sheila. Thank you.
Is it showing up and everything?
It is, yes.
Okay, so we've got California here and Oregon and Washington. We have 3 tectonic plates that we're dealing with. And so we call this point right down here, this is Cape Mendocino off the coast of California. We call that a triple junction because it is where 3 plates are coming together. The North American plate right here, which I have outlined in a dashed line. The Juan de Fuca plate, which is made of a couple little subplates as well. And the Pacific plate. And the Pacific plate is moving in a northwesterly direction. Okay. So here we have Cape Blanco. And here we have the Columbia River, and I'll put Portland in. I'll put a dot for Portland, which would be right about here. Okay. And this is what we've got going. Okay, so there's an actual Mendocino fracture zone, which is a mountain ridge underneath the ocean here, and it extends all the way across the Pacific, practically most of the way across the Pacific, and it acts as a funnel for any like an earthquake that happened in Japan will be coming down this way. It hits the Mendocino fracture zone and directs all that energy, that wave energy, right over to Crescent City, California, right in here. So we've got this Mendocino fracture zone, which is this whole line right here. Okay, but I just wanted to point that out. But we have 3 plates. We have the Pacific plate, the Juan de Fuca plate, and then the North American continent. Now, the edge of the continent is right here. This dashed line is the actual edge of the continent. So we don't count the continent by the shoreline that you're familiar with. We actually count it by this line right here. And this is the actual edge of the plate. This is Cascadia subduction zone. And it's about 60 miles off our shore. And we are concerned about a subduction earthquake. A subduction earthquake happens when one plate is slipping over another and pushing in. And this is where the plates are stuck right now. And when they do snap, it's going to cause a blister underneath the ocean and give us a tsunami very quickly, within 15 minutes of it happening. Okay, that's what we're afraid of. But we recently had earthquakes in this area here off the Oregon coast. Now let's look at the motion of what goes on. If I take the Juan de Fuca plate and I start moving it the way it moves, it does this. Okay, it opens up the spreading center here. This is where new ocean floor is being created. Lava is coming up, and this is what we call the spreading center. We worry about the plate subducting right here, going under the other one and getting stuck here. This is where we worry about the subduction earthquake. But the earthquakes that were happening offshore are in these locations, right here where my finger is, and right here. What are the plates doing in relationship to each other here? Well, they're not bumping into themselves like we have going on at the subduction zone. There's not doing this, and they're not spreading apart like we have at the spreading centers, which are right here. But what are they doing? Actually moving side by side here. So we have one plate. You can draw a little arrow here. We have one plate going this way, and because the Pacific plate is moving to the northwest, and in relationship to it, this little segment is moving in this direction. We call that a strike slip fault. Same thing down here in Cape Mendocino, same thing. So we've got an arrow here and another arrow here. Okay, so when plates are actually, these two segments right here are slipping past each other. Oops, I'm not spreading them right. There we go. So that we have a spreading center here and a spreading center here and more spreading up here. But in this location and this location, they're just slipping past each other. When two plates slip past each other, they get stuck on each other and they do create earthquakes. But these are not, they're not bumping the water and creating a blister that's going to cause a tsunami. So I just wanted to kind of give you a little demonstration like that to make it clear. Yes, you should be concerned about a subduction earthquake, but you don't need to be overly concerned every time you hear of an earthquake happening off the coast of Oregon. And that's all I wanted to say there. Just wanted to clear up some misconceptions that might have been out there.
That is a great relief, Sheila. Thank you for that explanation. I love the physical models in.
Gotta have the visual.
Yeah, you gotta have the visual.
Yeah.
Really helpful.
Okay.
All right. Any questions about Sheila's presentation there before we continue? I want to mention just briefly that I just put the legislative concept in the brief for the legislative concept 145, which is the name of the CEI bill before it becomes a bill, and it will have its bill number on Monday. But that's in there, and I'm going to contact those of you who've been expressed interest by email. A couple of you gave me email or said you were interested, and I don't have your emails. Diane and Sherry, if you could put your emails in the chat. Any
And
other
also,
questions for Sheila?
There is a question in the chat box that I just saw. So let's see, Shane mentioned that it is strike slip motion, and you are right. And John Ogden asked if they're pure transform or transpression tension. I have to say that almost nothing in nature is ever as simple as I make it sound. So yeah, there's probably a little bit of uplift with it. That of course we have strike slip faults all the way running through Oregon as well, and that's what's lifting up the Portland Hills, for example. So there is some. So I imagine, I don't know what's going on offshore underneath the ocean. Tanya does, but I don't. But there probably is a little bit of uplift there. You know, it's probably not quite as simple as I made it sound. But the basic concept is the same. It's strike slip, which isn't going to cause the bumping of the ocean floor that's going to create a
I
tsunami.
have a question.
Valerie has a question.
Yes, when you, I just wondered this week, because of the massive geological event of that volcano exploding and all the ash plume that went all over the world, did Oregon have, I haven't been reading the newspaper, but did we have a tsunami come as far as our shores? And do you, from an Oregon perspective, how did that affect us?
I'm wondering if Andrew's going to cover that.
Andrew may want to touch on that, but I will say yes. By the time volcanic eruptions do create a cause, in some cases cause tsunamis, and the tsunamis there locally would be a lot stronger. We did have a tsunami here on the Oregon coast, but if the wave is only 1 to 2 feet, 1 feet high, then it's hard to distinguish that from a high tide.
Sure.
Now, people will still go down there. And not that being said, a wave that comes in that's only 10 inches tall is enough to knock you off your feet if you're walking on the beach and, you know, doing that. But it wasn't any major thing to be concerned about this far. But Andrew, I'm sure Andrew will address that probably a little more fully than I did.
Yeah.
All right. Any
Okay.
other questions for Sheila before we pass the baton to Andrew? Shane, do you have a question?
I do, if you have a
Please.
brief. Could you, I guess, give me one thing that that has affected, well, okay, so let me rephrase. Could you explain a little bit how the transition from Farallon subduction to the northern migration of the triple junction with the Juan de Fuca plate, could you explain one impact on Oregon's geology from that transition?
Okay, from you mean the triple junction, or the Juan de Fuca plate is, oh, well, that's something else. That, do I have a minute to go back to the document, Cameron?
Yes.
Okay,
Yeah, let's.
all the time.
This sounds like a pretty meaty question, but I think it's fascinating.
Okay, well, what we have going on here is we had the Farallon plate. The Juan de Fuca is a remnant of the old Farallon plate. So this plate used to be much larger and it was subducting under. Okay, and North America, I taped it here to my table so it wouldn't move, but it is actually moving as well. So they're converging on each other right here. And most of the Juan de Fuca, most of the old Farallon plate has already subducted under the continent. So the only remnant that's left, we renamed it the Juan de Fuca. Did that answer your question?
Oh, I was more looking for like one significant geological feature of Oregon that is a result of that regime change, I guess. But that's okay.
Another thing I could mention is, well, that initiated, when this subducted fully, then that initiated the San Andreas Fault down in California. And I just got back from a field trip studying the northern section of the San Andreas Fault. And it is actually causing Oregon to rotate. This pushing at the triple junction here. This is where the San Andreas Fault comes up from California and actually enters the ocean right about here. And I went and visited that spot this summer on a field trip with Tanya Atwater, actually. And so we have this motion going on. And I think that is responsible for the rotation that we see in Oregon.
Good. And if you're interested more in these questions of what happened to the Farallon plate and all of the, and what happens when you get one of those transform faults subducting, Nick Zentner is doing fabulous work on his podcast and YouTube channels, and interviewed Dr. Karen Siglock this past week, or last Saturday, and that's all online. And he's doing, it's wonderfully fascinating stuff. It's 12:31. I'm going to pass the baton to Andrew and the geology news.
Howdy, everyone.
Welcome.
We've had a very interesting and exciting month as far as geology goes. I always love to be reminded that we live on a highly active planet that is always changing and doing stuff. And I love it when the planet does stuff. So let me jump right on into this week's, oh, that's the wrong button. Hang on. Seems to have disappeared from my share screen menu. One moment. There we go.
Good.
The menu out of the way. Alrighty, this is the geology news for January of 2022. Happy New Year, everybody. I always like to start out with earthquakes because I am an earthquake geologist, and this is a little bit of the 2021 in review as well. But the biggest event last year was located right about here. I don't have it on this map. It was a magnitude 8.1, a subduction zone megathrust earthquake here north of New Zealand. It was felt by about 8 people, according to the USGS, who felt it counter. Where people all around the world can submit whether or not they felt any earthquake. And that was the largest event of 2021. But the biggest event of January this year has been a magnitude 7.3 near Timor, which is an island in sort of the Indonesia area right here. And this was located at a pretty extreme depth, 165 kilometers below Romang, Indonesia, which is a tiny, tiny island, and Timor is just the largest population center nearby. And so this is occurring in the downgoing slab of the Australian plate as it subducts beneath. This plate has there's a little microplate here that has its own name, and I can't remember it right now. But we've actually detected earthquakes quite regularly down to 500 kilometers in this subducting downgoing slab as it disappears into the mantle. So that's pretty interesting. It did not cause very much damage at the surface because it is so deep below the surface. Unfortunately, there was an earthquake in China that did cause some damage. That's this one right here. It was a magnitude 6.6. There were a number of injuries and widespread damage, but this is the same fault, the Haiyuan's fault, which forms the northern boundary of the Tibetan Plateau. It goes right through here, through central China. And in 1920, an earthquake on this fault killed 250,000 people and just decimated all of this sort of central region of China. Quite horrible and tragic. But this small earthquake here, or I guess it's sort of a moderately sized earthquake that didn't kill anyone but did cause some damage, is a reminder that this is a tectonically active part of the world. As far as the United States exclusive economic zone goes, there was a magnitude 6.8 in the Aleutian Islands right here and a 5.9 here up on mainland Alaska. And there was a magnitude 6 in Cyprus right here, which is big for Cyprus. Widespread minor damage. There is a subduction zone here where Africa is subducting below the Anatolian microplate and the Eurasian plate more broadly. Some damage, no injuries or deaths that I have found. Oop, forgot to delete this slide. That's from last time. This is the United States for this month. This is all earthquakes in the US for the last 30 days. This is really standard background seismicity. The largest event was this magnitude 6.2 near Cape Mendocino that Sheila briefly mentioned. But this one actually did not occur in any of these surface structures. It occurred inside the subducting Gorda plate, which is a part of the Juan de Fuca. And it was not at all connected to the Mendocino fracture zone or the San Andreas Fault or the Cascadia subduction zone. It actually occurred below and away from all of those three different structures. And all of the aftershocks have also been inside that subducting slab of rock. There's also been a small continuing swarm of earthquakes in the New Madrid seismic zone and seismicity in Oklahoma and Texas related to the exploitation of gas fields. There was one that was particularly interesting to me, and that was, I believe, this one right here, a magnitude 4.1 earthquake in Eureka Valley, which is part of the broader Death Valley region that was felt across California. Nice small earthquake in the Walker Lane area. So I'm going to go into research now so that I can spend more time on the recent volcanic activity a little bit later. So I've kept my research section a little shorter this month than usual. A find in, oh, I forgot to say, a new fossil trove was discovered in Argentina that shows that these dinosaurs congregated in herds, which I think we already, we've mostly known that dinosaurs did sometimes occur in herds, congregate in herds, I mean. But this huge field of nests, including eggs and adult skeletons, dates to 193 million years ago, which predates the oldest known dinosaur herd behavior by more than 40 million years, which is pretty neat. 69 adult skeletons and 100 eggs of this species, Mosasaurus patagonicus, a ancestor of the sauropod, which later became things like brontosauruses and apatosauruses. I'm not super familiar with dinosaurs. Forgive me if I butchered those names. This one was of particular interest to me because I've studied some deep earth processes in the past, sort of for fun. But diamonds are one of the few minerals that can survive an ascent from the deepest interior of the earth up to the surface because they're so hard and durable and long-lived minerals. And sometimes, very once in a while, they carry inclusions of minerals from the deep mantle. You can see them. This is the diamond in question. It's about a centimeter across. And these black spots inside it are actual inclusions of minerals from the deepest mantle rocks. This new paper that was released was specifically about this mineral, Dave Mowite, which is a newly discovered mineral. It's been synthesized in the lab and hypothesized from chemical reactions and pressure interactions, but this is the first naturally occurring specimen of this mineral ever found. And it contained traces of uranium and thorium, the radioactive decay of which is what is the source of Earth's heat. It's obviously very hot inside the Earth, and the radioactive decay of minerals like uranium and thorium is the primary generator of that heat now. There's still some heat left over from when the planet accreted from space debris, but radioactive decay is what keeps it all going and driving things like volcanism and plate tectonics. So it's tough to say exactly what depth this diamond is from, but it contains other minerals. This one, woostite, which is one I wasn't familiar with beforehand, and a very high pressure form of ice that stays as ice at the surface because of the pressure it was formed at. But this particular one single rock is connecting the heat of the Earth, the deep high pressure of the innermost mantle. The pressure corresponds in certain areas to maybe a depth of 2,500 kilometers, which is just unfathomably deep into the planet. So it connects heat, pressure, and the water cycle all in this one diamond. So that was very cool, and people on Twitter have been very excited about it. Sticking with some, I guess, loosely tangentially water-related thing, the Chinese moonlander Chang'e 5 has sampled water in lunar soil. And this is part of the sample return. This mission had a sample return component that returned about 1.7 kilograms of lunar soil and rock back to Earth, which got back here just a few weeks ago. to China. Obviously, it's not here in, in the US. But this lander actually did the first in situ analysis of soil on the moon. And they were specifically looking at water content inside this lunar soil. So the chemical and physical interactions between the basalt on the surface of the moon and solar wind and cosmic rays can create trace amounts of water over billions and billions of years. I'm not going to get into the physics and the chemistry behind it because it was a little over my head. But it does match the water chemistry samples found in samples from the Apollo mission. So that's interesting. And it, just another way to show that, yes, we did go to the moon and retrieve samples from it. This one coming out of India was very interesting to me as well. In 1897, a quite severe magnitude 8+ earthquake shook sort of northeast India, Bangladesh, Nepal, this whole region of the subcontinent, which killed over 1,500 people and generated 33 feet of vertical uplift at the fault trace, which is incredible over the span of a couple of minutes. A mountain range uplifted 33 feet. But until recently, the exact epicenter of this earthquake was unknown. This sort of triangular area here, which a geologist, Oldham, created in 1899, was where he guessed the epicenter might have been. He couldn't quite figure it out. But there were just enough seismometers around the world back in the day that we were able to reconstruct sort of approximate times of arrival of seismic waves. They weren't, seismometers back then weren't quite as synchronized as they are today or as precise, but the margin of errors were close enough that we are able to establish the epicenter right about here using highly refined computer models to figure that out. And it was determined to be on a buried south-dipping fault. So it didn't actually reach the surface, even though the 33 feet of uplift was noticed and is observable. But most major earthquakes of this size, magnitude 8+, are surface rupturings. The fact that this one actually didn't reach the surface is quite surprising, very interesting, and has implications for understanding the seismic risk of these kind of buried little understudied faults in the Himalaya mountains. Very interesting. And just one more fun little fossil discovery. There was a huge ichthyosaur discovered in Great Britain. This is the largest one ever found in the UK. It is exceptionally well preserved at 180 million years old, found in the side of a drainage canal. And the skull is 2 meters long, bigger than this guy sitting here, which, if you don't know what an ichthyosaur is, it's kind of like an evil reptilian dolphin. So if you can think of that, then that's what an ichthyosaur was. All right, so now to volcanoes. And I'm going to build slowly to the big one I think we've all heard about by this time. There are 41 ongoing or new eruptions currently in the world. Some interesting notable ones. Kilauea is still doing its lava lake thing. Cerro Lobo, Wolf volcano in the Galapagos, has a new eruption. And there's been a lava flow at Great Sitkin up here in Alaska. Here's that Galapagos lava flow. It's called Wolf volcano in English. This is from the Galapagos Volcanic Observatory. And here's that lava flow in Alaska. This is an image from satellite radar imagery. You can see the pressure ridges from the rock as it flows down the side of the volcano. The vent is right here. And now the one you all want to hear about, Hunga Tonga Hunga A'api, which is a 2 semi-connected islands in the South Pacific of Tonga. This is the largest volcanic cloud since Pinatubo in 1991, and one of the largest ones ever seen by satellite. There's 2 little volcanic islands right in the middle of this cloud. And since about December, there's been a number of small eruptions. Eruptions have been recorded from this particular little island group for thousands of years, as long as the Tongan archipelago has been occupied by humans. But this is probably the largest known eruption from this particular volcano. Let's see, what's my next slide? Okay, here's what it looked like on January 7th of 2022. This is just before a steam eruption on January 14th, a smaller scale one. And this is what it looked like. Most of this island part here actually formed in December from a series of small eruptions. On January 14th, it looked like this. This was this is a large underwater volcanic eruption. You can see part of the island right here along with this ash cloud. And then on January 15th, this image is interesting because it just kind of looks like a blue sky until you see this part here, which is the edge of that ash cloud. This is early on in the stages of the eruption viewed from the island of Tonga. You can see part of the plume down here. So Hunga Tonga, Hunga Apali is right here. And then from space, it looks like this. The scale bar is 500 kilometers.
God.
I've watched this loop about 1,000 times because I just cannot comprehend how big the scale is. It's just enormous. Here it is with the planet Earth for scale.
Wow.
And the interesting thing here, you can see this is a shock wave. So when this volcano erupted, it exposed somehow, it could have been a small underwater landslide or an earthquake, but the magma conduit suddenly got exposed to water. And when you have basically a pipe of magma, maybe a few hundred meters across, suddenly exposed to the ocean, not only does all of the ocean suddenly turn into steam, but that entire pipe of magma, it's full of dissolved gases and fluids and all sorts of other stuff. But then it's like opening the lid to a soda can, and all of that explodes out as well. So you have the magma forcing up, you have the ocean rushing in and instantly turning into steam, and the combination of factors there created a giant steam explosion, which sent a shock wave that was actually heard as sound 1,300 kilometers away in New Zealand and 10,000 kilometers away in Alaska. This is the before and aftermath of that explosion. This is viewed from satellite radar so that it can look about the same. This is what it looks like. This is the same view as that satellite image I showed or a little bit earlier. And this is what it looks like now. The islands kind of went away. They got exploded. This is the best high resolution imagery we have so far of it. You can see pumice floating in the water here. That's what these brown streaks are. And when this happened, it created a tsunami that has impacted Tonga quite severely. We don't have too much information coming back from Tonga because the underwater cable that connects Tonga to the rest of the world got severed. So it's very difficult for them to get word out on exactly what they need. The neighboring countries have been sending as much aid as they can, but the airport is covered in a foot of ash and pumice. So we can't land planes there, and getting boats across the South Pacific takes a long time. So we're still waiting to hear about exactly what the extent of damage is. We know about 3 fatalities due to the tsunami in Tonga, and we know about a variety of injuries. The damage is enormous. Some of the islands of Tonga do not stand up very high above the ocean. And the tsunami, the wave was only about 1 meter high, but because of the energy it had, the momentum and the force behind it, it ran up to an altitude of about 15 meters. So everything below that has been severely, severely damaged. Most buildings are only 1 story. So that's quite, that's a recipe for disaster in Tonga. And I'm certainly waiting to hear more about the shape of things over there. We know it's not good, but hopefully there's not too many more fatalities. This is that pressure wave, that shock wave, measured in Iceland. So this is the first time it came around. It's kind of 2 peaks here, and it went around the globe 3 times. The reverberations from this giant explosion went around the globe 3 times. And I'm going to go back a little ways. I guess I didn't include a world map of where this is going on.
Mm-hmm. A quadruple junction.
Yeah, well, Tonga itself is on top of, it's in the middle of the Tongan Trench, which goes right about here. Now let me, I'm actually going to pull up my Google Earth. because that will be helpful.
One of our board members heading out to the South Pacific even as we speak, but I think she's headed to a different trench perhaps. That's Dr. Emily Cahoon.
Yeah, she's going out of Hawaii. She's studying seamounts, not trenches. I didn't know she was on the board.
Is that what it's called? She and another student, you may know, Tiana Casey, are headed out
Nope.
to look at some of the oldest basalts out there. Beautiful. Thank you, Andrew. That's looking good.
Here we go.
We're seeing
Okay, so
it.
here's American Samoa. Tonga is this island chain here.
Wow.
And this is the deepest, one of the deepest trenches in the world, the Tongan Trench.
Mhm.
That quadruple junction that Sheila mentioned is, I think, this one up in here. So the volcano that erupted is located, where is it? It's one of these. Oops, Tofu. Thought I had a mark. Nope. Nope. Either way, it's located in here and it's a underwater volcano. You can see in sonar imagery, it's just a mountain. But on top of that mountain, it's flat, and it's not flat because coral atoll, it's flat because it's a volcanic caldera 5 kilometers across. And volcanic eruptions happen all around the rim of that caldera quite frequently. So the tsunami impacted Tonga, but because of these islands here, those sort of shielded this tsunami from impacting Fiji, the Philippines, or Indonesia worse than it otherwise could have. But there's no islands in the way over here. So the tsunami impacted the west coast of the United States. Let me turn some of this stuff off. There was actual significant damage in Ventura, California, Port San Luis Obispo right here, Crescent City, and waves are recorded traveling up creeks all along the Oregon and Washington coast, and was recorded in some of the fjords and inlets up here in southern Alaska, northern British Columbia. But the tsunami here was a combination of factors. It was not only from the actual volcanic explosion itself, but the shock wave, the atmospheric pressure wave, pushed the surface of the water to create a seiche wave, it's called, all the way up across the Pacific Ocean up to Alaska and California and Oregon. That was about a meter in certain places, and the elevated water levels lasted hours after the initial volcanic explosion. So this is, there's been a lot of chatter on the internet, people asking, is this volcanic eruption big enough to cause atmospheric climatic changes? No, is the answer to that. This volcano is basically an order of magnitude too small to have any sort of global climatic events. Pinatubo in 1991 famously spewed enough stuff into the atmosphere to have about 1.5 degrees Celsius of global cooling for a couple of years. This one is just way too small to be able to do that. So unfortunately, no global cooling event from this volcano, but it was certainly, it will probably remain as the greatest volcanic event of the decade. This is a very rare and very cool event. And hopefully everybody in Tonga ends up okay. That's all I have for the geology news for January 2022. Thanks to all for listening.
Thank you.
Well done.
I'm not.
You're muted, Paul.
No one. I was muted. I muted and unmuted myself. That was wonderful. We've got 6 more minutes and 4 people who have something to share geologically. If Andrew, if you can stay after the hour, there might be some other questions. But I want to, those of you who volunteered, you can come back next week and we can, we always have a little extra time at the end if you want to share. But we have some folks from out of state who have some information and or who have something to share with us. Is that the way I want to do it? Do I want to try to rush people, or do I want to give people a chance to ask Andrew another question? I don't know. We're sort of feeling our way through this thing. And one of the
I can
things
do
that
questions after.
you could do questions after. One of the things I like about exactly this size is everyone kind of gets to know one another and there's a chance to hear everyone's voices. Okay, Andrew's willing to do questions after. So let's go to our shares, our show and tell. And I think, Gary, are you still here? Who is the first person to put into the show and tell?
Oh, John Ogden?
All right. Well, what does John have to share with us?
Hey, good afternoon, folks. Or good morning, I guess, for you. I have a box of rocks, and I'm not going to share them all with you. I will pick one.
Pick one, one of your favorites, and just tell
Yeah.
us what it is and what the story is.
Okay, here, hang on. Well, this one's standing out to me. I'll just bring this out here. Let's see if I can successfully turn the camera around here. Let's try that. Oh, look at that. There's a rock.
That's a rock.
This is a piece of the Conestoga Formation, which I collected locally. I kind of head out and try and find a sample that's characteristic of the formations in the area, because I'm trying to learn a little bit about identifying rocks. So this is supposedly a marble.
Oh,
So it's marble with mixed into a kind of a schist matrix. It's all metamorphic. It's an interesting thing. Conestoga Formation, if you want to look it up.
so it's a carbonate rock. It's marble. It's a former limestone, metamorphosed limestone, but it's got schistosity in it, or
That's my understanding, because
okay.
most of what I come across is schist, and you can see the blue streaks in here. It's a weird rock, and
It's
I've
a
never
weird
seen
rock.
anything like it.
I love a
Have you put
weird
acid
rock.
on it to see, does it effervesce? It should effervesce with hydrochloric acid.
Unfortunately, I don't have any acid, so we'll have to take their word for it.
That's a great rock, and we
kind
can.
of a soapy feel to it, like a soapstone.
Okay.
Uh,
All right. Well, that's perfect. Stick around. Then after the hour, we can circle back if people have more questions. Who is
Gotcha.
next with the show and tell? Gary?
Oh, yeah, I have to check out.
That's right. You've got to go and work on a project. So is Shane the next person we've got here?
Yes.
Okay. Thank you, Gary. And thank you for all your work. It makes it so
Gary.
much easier for me to have you minding the back end. So
You're
have a
welcome.
good day. We'll see you next month. Shane, what have you got for us?
So I don't know if you guys can see this very well. This is a gypsum twin that I picked up outside of Jean, Nevada. If you guys know where that is, it's about 25 miles south of Las Vegas. There's an evaporite deposit there. And so this is a clay and gypsum gyprock, is the backside. But this was the biggest twin that I could find while I was walking out there. So if you guys see, this is one gypsum crystal. And going that way, that's another. And they have a little line in the middle where they're twinning.
Yeah, cool. Very
Looks
cool.
like a heart.
Can you scratch it with your fingernail?
Yes, I sure can.
What causes the twinning?
Well, in an evaporite, it's just two crystals growing together, basically. They share a nucleation site, you know. Nucleation being the chemical process that comes from the evaporation of water. And it would be different if it was a hydrothermal gypsum, theoretically, I guess. But yeah, that's my understanding.
That's lovely. Thank you. And we're going to go to Roxy, who has something for us.
Okay,
And then Wes.
my husband's gonna shine a light on this. So you can see the organic, the curviness in there. Oops, oh,
Low battery.
sorry, I have low battery.
We can get you plugged in.
Okay,
We can see it.
anyway, this is a stromatolite. You can see the kind of organic curvy stuff in there. We were on a geology trip looking at something else. It's just reflecting So
Where
it's
did you
not,
be
that's
like
not,
that?
that's not helping. That there.
Maybe that's
See that
better.
curviness in there,
Yes.
that organic stuff? Anyway, we were on a geology trip with a geologist who discovered the site where stuff landed in northeastern Minnesota from the Sudbury impact. And we were looking at that stuff, and we were looking at all these lapilli that rained down and got stuck in the earth. And right there was a whole bunch of stromatolites as well. Now, most of them were stuck in the bedrock, but this piece was just sitting there loose. So of course I picked it up, and it wasn't.
How old do we think it is?
Oh, billions, maybe?
Billions of years old.
Steve, can you help me? When did that happen? When did the Sudbury impact happen?
Can you hear me? Okay,
Yes, we can.
okay. Sudbury, I think it's 1.5 billion. Last I think I heard. So it's a very, very old event. And it was quite a devastating deal. They actually found a layer of rock, I think about 6-8 feet thick on the far end of Lake Superior. Sudbury's on the eastern end, and this is on the western end of Lake Superior. So a couple 100 miles, and you still had a big, thick, 6-8 foot layer of rock that was formed from it. It was an interesting thing because a couple of earth science teachers from, I believe, Thunder Bay, just junior high school teachers, started going out looking for it. So even the people who are not professionals in the strictest sense can still contribute to geology. It's one of the things that I like about geology. You don't have to necessarily have a PhD to be an important factor in it. So
That is fascinating. Thank you, Roxy. And last we have Wes. Wes, I know you got a carnelian for us. We're 2 minutes over our time. So if you could just show it, and then we'll turn off the recording. I go to check the oil in the internet, and Sheila, I'll sort of hand the hosting over to you, and people can talk and ask Andrew questions and ask Roxy and John and Shane and Wes questions if you have them. Go ahead.
Most of you probably know that my son owns a Rockhound coffee shop, and Andrew knows him, Luke. And they just opened an annex, so he's got twice as many rocks on display starting last week. But carnelian, I thought, usually think you have to go out in the woods to find carnelians, but I have a house in Selwood, and I was walking down the sidewalk, and I see this sidewalk verge full of landscaping rock. And I look down, and I see this, which maybe on a dark, cloudy day wouldn't look like anything, but it's a huge piece of carnelian. And on 3 subsequent walks, I have found big chunks of carnelian agate there. And I just wanted to encourage anybody, don't always look ahead, look down sometimes. Landscaping rocks, if you find any patches of landscaping rocks that aren't rounded basalt river rock, stop and have a look, because you're likely to find something very fun and interesting there.
That is so true. I spend a lot of time looking at any kind of rock that comes into my field of view. Well, it's 1:04. We've done pretty well today as far as me keeping things on time. I appreciate everyone's contribution. I'm going to turn off the recording, and just because don't want you to feel like you have to stay past the hour, but if you have questions for Andrew or John or Shane or Roxy or Wes or Sheila, stick around, and we'll have the room open for about half an hour.